Behind that firewall coming out of the trombone, you see two 4-cylinder engines that are capable of revving to over 15,000 RPM. And these two engines are chained together. I've connected them with the special rear axle to allow them to spin at slightly different engine speeds. Getting the RPMs very close to each other but not perfectly even should create an interesting acoustic effect called beating. The other option to chain them together is via the crankshaft. This would allow to adjust the timing of these two engines in such a way that they would release their exhaust pulses almost like a super high revving inline 8-cylinder. And wouldn't that be the perfect test engine for different exhaust designs in the future? But getting a chain to spin at 15,000 RPM is not for the faint-hearted. But if you're interested on working on engine projects with a shoestring budget, don't mind the abuse of musical instruments, and are not scared of failure, you've come to the right place. This project actually originated way back in 2015. After failing to get my V12 engine swap Nissan to sing like a Pagani Sonda, I was thinking what most people would think. It needs more RPM. Little did I understand back then about the complex exhaust resonance tuning that's required to get a V12 to sing like an old Formula 1 car.
What we now call R1FO tuning.
So instead of fixing my knowledge gap, I started hoarding these high RPM 4-cylinder engines, which were back then plentiful and cheap, especially if they were slightly broken. But the biggest issue is, how do you combine those engines into one single unit? I planned on using rubber dampers to stop the harmonics from building up in such a long crankshaft, but I didn't even get that far. When I started with this project, I used carbon fiber to create a cover plate and get access to the crankshaft. These carbon fiber engine covers never stopped leaking oil from the radial shaft seal, and that was a problem I could not overcome until very recently. But I'm getting ahead of myself. In the background you see my friend Tim trying to fix his broken V12 that suffered from bearing damage by retrilling bearing shells that were made for a different engine. But let me tell you, it didn't work. In the foreground, I'm preparing one of those 4-cylinder engines for a 3D scan by a method called photogrammetry. This is where you take hundreds of photos from different angles, and with the help of some specialized software you can recreate it as a 3D model in a virtual environment. And this makes it very easy for me now to design the rest of the parts I need to complete this project. But this time I made a significant change in how the crankshafts are synchronized. Instead of transmitting the power from one end to another, I added a chain-driven check shaft. I was a little bit concerned that even a slight misalignment between the engines could cause a catastrophic engine failure, especially at high RPM. But connecting two shafts spinning at 15,000 RPM with a chain is not exactly problem-free either. Imagine wrapping a chain around the disc of an angle grinder and letting it run at full speed, and then adding another close to 5,000 RPM to it. The centrifugal forces alone trying to rip the chain apart will be immense. But this chain should be able to handle it. Maybe. I started with the design of the sprocket adapter that would fit the snout of the crankshaft. Then I added the engine cover, the shaft seal and the bolt-on shaft seal housing. This engine mount formed a part of the checkshaft assembly. This included adjustable sprocket dials, sprocket adapters, checkshaft bearings and the bearing housing, plus some chain tensioners. On the gearbox side I added a relatively simple rear axle with some wheel hubs and bearing adapters, as well as sprocket carriers that double as differential housing. This should allow me to test the engine under load. To top it off, I designed this very fancy looking gear shift lever that I wanted to get 3D printed from metal. For the exhaust I designed this adapter and added a pair of 4-into-1 collectors and a Y-pipe, all of which are available straight from the exhaust collector catalog on my website. So while I'm downloading these collectors, let me show you how to turn these designs into reality. The sponsor of this video, JLCCNC, makes that possible. You simply upload your designs to their website and get an instant quote for a really good price. And when you order your CNC machined or 3D printed parts, you can choose from many different materials. After I've uploaded my design, I was honestly a bit skeptical, because I've designed the bearing housings for the track shaft to be an interference fit. So they have to be machined to extremely tight tolerances, but that also meant I've had to upload a technical drawing. But to my surprise, even my amateurish drawings were approved in no time. But if you are on a real tight deadline, your order can be prepared in as little as 3 business days. And JLCCNC offers shipping to countries all over the world. So as soon as my order arrived, I couldn't wait to test fit the bearing housings. A machinist once taught me a neat trick, which makes the assembly of interference fit parts a breeze. You not only heat up the bearing seat, but put the bearings into the freezer. See you in a couple of hours. With the right tolerances, they will almost slide in. And once the temperature stabilizes, they will be locked into place.
Wow.
The 3D printed gear lever was another surprise. I designed it with such thin sections that it actually triggered a warning. But in the end, I was really impressed by the way it turned out. You should definitely give it a try for your project and check out the link in the video description. But before I could make use of the shifter, I needed to combine these engines first. By using CNC-machined engine mounts, it shouldn't be too hard to get these engines aligned properly. Thank you JLCCNC for making fabrication so easy. Almost too easy. So to make things more interesting, the fabrication from here on follows a simple policy. Whatever else I need for the fabrication, but if I can't find it here around the garage, I can't buy it. But with plenty of piping still laying around, I wasn't too worried. At first. I designed the engine mounts out of steel so I could easily weld some stuff to it if needed. And with some braces welded into place, they became very stiff. But of course, this ease of fabrication wasn't to last. It didn't take very long for the first problem to show up. One of the engines I'd salvaged had previously had one of its exhaust mounting points ripped out of the cylinder head. There was actually a gaping hole before, and that had only been fixed with some JB weld years ago, but it started to crack again. That means that just tightening down the headers later on could whip a hole into the cylinder head. To reduce the chances of this happening, I temporarily fixed it with some more JB weld, which should at least allow it to survive the first couple of tests. But before these tests could happen, I needed to get rid of this old leaking carbon fiber engine cover and replace it with a precision CNC machined, hopefully non-leaking one. But the shaft seal in combination with the self-centering bolt-on shaft seal housing should take care of that. The rear half of the sprocket adapter provides a much better surface to seal effectively than the conical shape of the crankshaft snout. Now all that's left to do is adding the sprocket, clamping it down, and the first engine is basically done. And except for the removal of the alternator, the procedure was almost the same for the second engine. Engine cover, shaft seal housing, sprocket adapter. Sprocket, done. With all the essential parts fitted, the engines lined up nicely. The reinforced engine mounts made it extremely easy to mount the engines to a pipe with some hose clamps. Everything so far worked just out as planned. But it's very unfortunate that I didn't spend more time planning ahead. Beyond the fitment of the relatively simple rear axle. Basically, I wanted these engines to be able to run in different gears.
We have a kind of open differential.
I thought I needed this. If you force the crankshafts of two engines to spin at the same speed, but force the gearbox outputs to do the same, it takes just one misshift and something has to break. So to prevent this from happening, I came up with this solution.
So this is attached to one half of the shaft and the other two halves are going to be attached to the other two.
In theory, this was a really good idea.
And this is going to be the wheel hub.
The rear hubs are meant to attach the brakes so I can run the engines under load. The brakes were borrowed from this car, which featured in a previous video of mine. With no engine left, it also needed no brakes no more. Attaching the rear axle to the frame was pretty much straightforward. The CNC machine parts just slid into place. But to clear the brakes, I measured how much of the axle should be sticking out to mount the rear hub, while listening to the smash it hammer at home.
So unaware.
While I was so unaware, I was lining up the sprocket of the rear axle with the gearbox output shaft.
So unaware.
So after welding everything into place, and everything was running nice and true, I had a problem. Actually, I had more than one, but I didn't know that yet. For the differential to work, the left and the right half of the rear axle have to be able to spin independently from each other. So they needed to be cut in the middle. After cleaning up the weld and reassembling the rear axle, the differential worked. Then I noticed something else. It's not running quite as good as before. But that was no problem.
That's so much worse.
After getting it back into an acceptable shape, I noticed problem number 2. The left half of the rear axle was now too short. Somehow someone must have been really unaware while taking the measurements. I extended that half with a pipe sleeve and had to repeat the previous process 2 more times.
The pain, infuriating, like just the most obnoxious process ever.
Moving on. After fitting the wheel hubs and the brakes, it was time to take care of the control center. This thing that is kind of shaped like a ladder is actually an exhaust from a previous test, but it would also make for a good seat mount. I also found the perfect brake pedal for it. If ever needed, it would also allow to brake the left and the right engine independently from each other. For the throttle I went with a used Nissan throttle pedal. They work reliably and hassle-free, and it was very easy to mount. To figure out the clutch system was quite a bit more complicated. Very often the most simple solution is the best solution, so instead of spending a lot of time figuring out how to build a hydraulic to dual engine clutch cable converter system based on used mismatched brake master and slave cylinders, only to then find out that the hydraulics didn't pleat properly, not even when trying to force the brake fluid with a syringe from the back end into the system, which would probably only result in spilling brake fluid all over myself, just to find out in the end that the brake master cylinder itself is broken, was too much of a risk and way too complicated. So I went with a cable clutch system right away, and I got it right the first time. A similar system was used for the throttle, but with the added issue that I was running out of cables. I still found these 2 from a Kawasaki exhaust though, which were just long enough to fit. For the brake reservoir, this airtight plastic container was perfectly suitable. So with the throttle, clutch and brakes working, it's time to mount the jackshaft. And while I was figuring out the right board lengths, the fabrication of the shaft and the right adjustments, I was thinking back to what I heard about the chain-driven camshafts in high RPM performance cars recently.
Yeah, once you go above 10,000, chains don't live. They don't work.
Although most bike engines rev higher and still use timing chains, these chains don't have to transmit a lot of force, therefore they can be tiny and light, therefore G-forces will be less of a problem. This is really making me a bit worried. However, for low RPMs it should still be fine. After getting the timing disc mounted, the frame received the fastest paint job ever. And it's done. Figuring out the wiring was next, but that wasn't too hard. I had these engines running before, but bike electrics sometimes have these awkward quirks like tip-over sensors. So if the sensor does not point up in the upwards direction, the engine won't start. There will be no spark, indicated by this blinking light, as I know now. And fixing the tip-over sensor to the frame fixed the sparking issue. Easy. Another issue was the sticking electronic throttle bodies on the right engine, but that's very common with these type of engines and they often get removed entirely. For the most part, this is nothing to worry about for my purpose. The fuel system was pretty much already built for a bike engine in a go-kart. The only modification required is that it now needs to feed 2 fuel rails instead of only 1. But with both engines sparking and fuel flowing, it was time for a quick test start. Wondered where this bolt went. I might have forgotten to tighten it down. During the trial fit of the exhaust, I noticed that parts of the pipe that hold these engines together might be in the way. I thought the engines would be stiff enough to handle it, so removing was an option. Therefore, the throttle and clutch mechanism also had to be relocated. Next up were the headers. And for the fabrication, I found this magical reservoir full of 90-degree stainless steel elbows perfectly sized for header pipes, including some cutting jigs and measurements. It's almost like these were ordered years ago for some project or something. But I've already built a header for exactly that kind of engine before for some exhaust tests, and I still had the jig to build more. And the cut list. The 3D printed collectors and the 3D printed Y pipe in combination with the adapters for the exhaust made the fabrication of the headers way easier and faster. I just cut up the individual pieces of pipe according to the cut list and then put them in the jig before I tack weld them together. And then completely finish off the welding one by one. For this project I won't flood the header pipes with welding gas. I have to use it sparingly, there's no buying extras, and it's also way faster this way. The collectors were slightly oversized for the primary piping I've had, but maybe that might be useful for something, someday. To keep the collectors from falling off, I've drilled a hole into the side of the inlet and spot welded them to one of the primaries. That shouldn't crack easily, but if it does, it's still kind of mechanically locked into place, at least when the primaries are sized to match the collector inlet size. My bigger issue was that I almost couldn't find any pipe around here that would fit the collector outlet and the Y pipe, except for these two stainless steel bands and just a half meter of super thick walled mild steel pipe, but a lot better than nothing. The exhaust was almost finished, but there was one more thing. I've prepared this adapter for a special reliable exhaust system, but I don't think it will sound that good. But I kind of like the way it looks. I think this modified KTM 2-stroke exhaust would sound much better. But before we can hear that, there's still a very important part of the build that's kind of required, the cooling system. Now for these two engines, I've had only one radiator that would fit. But more important than the amount of radiators is how much air you can force through them to keep them cool. A fan shroud that covers the entire surface and is sealed to the radiator in combination with the biggest fan that fits, well I can find, usually helps way more to keep temperatures in check than big radiators with poor airflow through them. In addition, I also fabricated some adapters to get the coolant to flow from two engines into and out of a shared radiator. After getting the cooling system hooked and filled up, it was about time to warm up the engines. And boy did they heat up. Getting the cooling system to work proved way more difficult than I had imagined. After bleeding the cooling system multiple times, I was already checking water pumps.
Well, it's turning.
The engines were fine before when I last used them, so I found it a bit weird, especially that after refilling the cooling system, the engines would take turns in overheating first. It took me a while to realize that these ripples in the hose are really good air traps. And a nightmare to bleed. To not overheat one of the engines by accident while bleeding the system, I thought it would be smart to remove the jackshaft and warm up each engine individually until the entire cooling system was air bubble free. And with the air out of the system, it actually worked really well. But there was one more thing left to fabricate. Now mounting the shifter was the easy part, but I didn't have the cables to fit the fancy designed shifters. And with the no buying extras rule in full effect, I had to figure out something different. After a really short and frustration-free 2 days, I finally got something that was working. But it's not this one. The first version had way too much play in the linkage. There's still a lot of room for improvement, but version 2 was already doing much better in that regard. Just the engines didn't really seem to appreciate my contraption. Every time they were put into gear, they instantly shut off. That was caused by another one of those quirky bike electronic safety features. I didn't have all the electronics of the bike, but I could figure out a way to trick them. Installing a jumper wire between 2 pins of the gear position sensor tricks the electronics into thinking that the engines are neutral all the time. At that point it was time to put the whole assembly through a durability test, before I reconnect the crankshafts. This takes some re-engineering. After inspecting the damage, I found that a weld has failed that connects the inner disc of the differential with the left half of the rear axle. Even after rewelding it once more, it remained the weakest point and almost failed immediately when I really leaned on the brakes. To get the rear axle into a reliable state, I had to make a change. I removed the differential altogether and gave it another try. But before anything else could fall apart, I really needed to see that musical exhaust in action. The damage was severe. Somehow the chain had forced its way through the water pump and taken out the clutch mechanism along the way. It seems like even without the differential, this entire assembly was flexing so much under load that the chain could jump right off the sprocket. Lesson learned, but how do I fix this? After checking the inside of the engine for broken metal, there was some glimmer of hope, although under the no buying extras rule the clutch was unfixable. But I still had a third water pump from the engine that I 3D scanned at the start of this video. I wasn't done yet. Only that stream of oil pouring from the engine tried to convince me otherwise. But once that hole was plugged, the cooling system refilled multiple times, the check shaft reinstalled, and the engine synced up with the timing light. It was about time to see what kind of RPM these chains could really handle.
Yeah, once you go above 10,000, chains don't live.
They don't work.
But first I went easy on the RPMs. It looks like the JB weld is cracking again. That's exactly where the smoke is coming from. Something is off. I could feel that the engines were clearly struggling at higher RPM. Something was definitely holding them back. Checking the footage, it looked like the chains were grinding against something. It looks like I didn't account for the washers under the bolt heads in my construction. Oh, shit. If the chain links grind on the bolt heads at over 150 feet per second, that would certainly introduce some amount of drag. Removing the washers was easy, but replacing the chains was not. I've only had enough new chain left for one more cut. But what about the other one? It already had a few chain links getting stiff from the heat. Is that really safe to use at 15,000 RPM? The conclusion I kept arriving at is yes, because I really want to try the two-stroke exhaust. But there's something you should know about me. I'm not a mechanical engineer, not a certified machinist, and not a professional welder either. But after having worked on this project from start to finish, in all of its details and nuances, and taking into account every fabrication challenge, the cooling system nightmare, and every quirky bike electronic safety feature, as well as the delicate harmony between the crankshaft, the jackshaft, and the twinkling supply of spare chains, I have come to the undeniable conclusion that I have nothing further to add, except, as I mentioned at the beginning, I am indeed not a mechanical engineer. That was the moment when I realized cutting that pipe that supported the engines was not a good idea. On the heavy load, the engines twisted so much that it caused the chain to spark on its own, without rubbing against anything. To not risk any further damage, I have to conclude for now. Over 10,000 chains don't live. Yet.